Hi friends, in this video we are going to discuss about the previous gate question. Right sir, next question. Let's see, a single phase alternator has synchronous reactance 2 ohms and resistance negligible. Synchronous reactance 2 ohms and resistance negligible. If it supplies 10 amperes to a purely capacitive load at 200 volts, purely capacitive load is very important here, then the generated EMF will be dash volts. And what is the voltage regulation? This is our question. Tell me, what is the formula generally? Generally, EMF E is equals to V plus IA ZS. But here RA is equals to 0. That's why ZS is equals to XS. ZS is equals to XS. That's why if ZS is equal to XS, what is the impedance angle theta? Impedance angle theta is equals to tan inverse of XS by RA, X by R. Something by 0, infinity. When we can get infinite? When theta is equals to 90 degrees. Yeah, when theta equals to 90 degrees. Purely capacitive load, nothing but what is power factor angle? 90 degrees leading. Purely capacitive load, 90 degrees leading. My impedance angle 90 degrees. Then my EMF E is equals to V at an angle 0 plus IA at an angle phi into XS at an angle theta. XS at an angle theta. Now tell me, what is our answer? EMF E is equals to 200 plus 10 at an angle 90 degrees and XS 2 at an angle 90 degrees. What is EMF? 200 plus 10 into 2, 20 at an angle 180 degrees. 90 plus 90, 180. Don't multiply here. We have to add the angles. Now tell me, what is your answer? 200 minus 20 is exactly equals to 180 volts. Sir, why it is minus? Yeah, why it is minus? 180 degrees, nothing but minus, right? Yes or no? Right. Okay. So our voltage is 180 volts. What about voltage regulation? Yeah, tell me, what is the answer? Voltage regulation is equals to no load voltage minus full load voltage by full load voltage. Now tell me, what is your answer? 200. Sorry, what is our no load voltage? 180. 180 minus 200 by 200. So tell me, what is your answer? Minus 20 by 200. Nothing but minus 10 by 100. Minus 10%. Minus 10%. Sir, why it is minus? Because it is negative. Because it is capacitive load. In alternator, if the load is capacitive, if the leading load, the voltage regulation most probable is the negative only. So what is our answer? Our voltage regulation is negative 10% and our EMF is 180 volts. A very simple question. Right, next question. Let's see here. See here, synchronous generator connected to infinite bus. Overexcited condition. Considering only the reactive power. Don't go for active power. From the point of the system, the machine acts as A. Yeah, see, generally for synchronous generator, reactive power is equals to V by Xs into E cos delta minus V. Actually, this is a reactive power for our generator. When this is connected to infinite bus bar and overexcited nothing but E cos delta is greater than V. When overexcited, when E cos delta greater than V, our Q is perfectly positive only. If Q is positive, it nothing but it delivering the reactive power to the system. The alternator delivering the reactive power to the system, delivering the lagging reactive power or observing the leading reactive power. Yeah, so whatever it delivering the reactive power, which delivers the reactive power? The capacitor delivers the reactive power. So our answer is a capacitor. The machine act is a capacitor because Q is positive, Q delivering to the system. That's why here the machine is nearly equals to a capacitor. Right, let's see the next question. The armature of a single phase alternator is completely wounded with C T singleton coils. Single phase, completely wounded T singleton coils. Distributed uniformly. The induced voltage in each ton is 2 volts RMS. Be careful. The EMF of the whole winding. Yeah, tell me, what is the formula for EMF of the whole winding? EMF of the whole winding, nothing but we have to find out ERMS for whole the winding. What is the formula for ERMS whole the winding? 4.44 into 5 into F into T into KP and KD. 4.44, 5, F, T, KP and KD. So right, this is the answer. So now we have to substitute all the values. Tell me, what is the KP for this question? What is the KP value for this question? For this question, KP is equals to 1 because it is completely wounded. Yeah, good. What is the KD for this question? For this question, KD is equals to 2 by pi. How it is? Yeah, it is uniformly distributed. For uniformly distributed winding, for single phase, KD is equals to 2 by pi. For 3 phase, KD is equals to 3 by pi. For 2 phase, KD is equals to 2 root 2 by pi. You can calculate this from the formula. So, for uniformly distributed winding, you have to remember these words. For uniformly distributed winding, for single phase KD 2 by 5, for 3 phase 3 by 5, for 2 phase 2 root 2 by 5, but they given single phase, that's why 2 by pi. And what is number of tons for this coil? They given T singleton coils. T coils each 1 ton. T coils each 1 ton. Yeah, okay. Now what about this? They didn't given the frequency and the flux. How we can calculate this value, sir? But they given voltage in each ton. Voltage in each ton, nothing but ERMS per ton. ERMS per ton. They given ERMS per ton. What is the value of ERMS per ton? 4.44 into 5 into F ERMS per ton. ERMS per ton, they given 2 volts. So its value 2. Now tell me what is finally whole ERMS. Whole ERMS is equals to 2T1 2 by pi. This is our answer. Nothing but what is the answer? 4T by pi. 4T by pi. Nothing but 4T by 22 by 7. 4T by 3.14. If you calculate this value, you can get 1.273. 1.273. Nothing but our answer is option D, 1.273 into T volts. 1.273 into T volts. Right, next question. Higher synchronous reactance is preferred in the present day alternators because one can have. Because why we are using high reactance? Why we are using high reactance? They may ask you a question, why we are using high impedance also? Why? Because generally we know that I short circuit current is equals to E by XS. If the synchronous reactance is high, automatically the currents reduces. Short circuit currents are generally the transient currents reduces. So why we are using with the high synchronous reactance or high synchronous impedance? In order to reduce the transient currents. That's why nowadays for alternators we are using with a high reactance or high impedance. This is our answer. Let's see next question. This is very, 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 very important question. Regularly and repeating question. A three-phase alternator is wounded with 60-degree phase spread armature windings and develops 300 kVA. If the armature is reconnected to utilize all the coils for single phase operation with a 180-degree phase spread, three phase operation with 60 degree 300 kVA, single phase operation with the 180-degree phase spread, then what is the new rating of the alternator? Nothing but we have to find the kVA for single phase. We know the kVA for three phase. Generally, the kVA is directly proportional to KD. The kVA is directly proportional to KD. Distribution factor. So, for kVA single phase to kVA three phase ratio, the ratio sine m beta for single phase, sine m beta by 2 for single phase, divided by sine m beta by 2 for three phase. This is for single phase, this is for three phase. Multiplied by. Here we have to take for three phase 60 degrees, for single phase 180 degrees. After calculating whole, we can get these values. Now tell me, what is the answer? Here sine m beta for single phase m beta is 180. 180 by 2, nothing but sine 90 divided by sine 60 by 2, sine 30 into 1 by 3. So tell me what is the answer? Sine 91, sine 30, 1 by 2 multiplied by 1 by 3. So its value is 2 by 3. Where the kVA of single phase to the kVA of three phase. Now if you're solving this one, 3 ones, 300s, so the kVA of single phase is equals to 200. kVA of single phase is equals to 200. kVA of single phase is equals to 200. Yeah, this is our answer. This is our answer. Here, the main thing you have to remember, kVA single phase to kVA three phase, we can write this line. For example, let's see if they ask you the kVA two phase to the kVA three phase, how you can? Tell me how you can perform these calculations, how you can. So first, sine m beta by 2 for two phase divide by sine m beta by 2 for three phase multiplied by, for three phase, what is m beta actually? For three phase, m beta 60 degrees, and for two phase, m beta 90 degrees. For two phase, m beta 90 degrees, for three phase 60 degrees. For example, if they will ask you a question, the kVA for three phase to the kVA for single phase, how you can? Now tell me how you can. We can write this sine m beta by 2 for three phase, sine m beta by 2 for single phase multiplied by, for single phase m beta 180 degrees, for three phase m beta 60 degrees. You know, m beta is equals to 180 degrees divided by number of phases. M beta is equals to 180 degrees divided by number of phases. For three phase, 180 by 3. For two phase, 180 by 2. For single phase, 180 by 1. For three phase, 60. For two phase, 90. For three phase, 60. For single phase, 180. For single phase 180, for three phase 60. This is the simplified formula. The simplified formula. Right? So this is the answer. We can write like this. You can find any answer by using these formulas. One, see, these three are very important for us. Let's see. Next question. The phase sequence of a three-phase alternator will reverse. Then what happened? Then reverse. Three-phase alternator, the phase sequence of a three-phase alternator will reverse if. What we have to do to get the reverse phase sequence in the alternator? What we have to do? Generally, torque is directly proportional to phi s and phi r. The torque is directly proportional to two fluxes, stator flux and rotor flux. To get the reverse flux, we have to reverse the torque. Or simply, if the stator flux is reversed, then torque reverse. If the stator flux is reversed, then the torque reversed. Simply, stator flux reverse nothing but phase sequence reverse. Phase sequence reverse, then torque reverse. Or by changing the torque direction, we can change the phase sequence. So what is the conclusion? By reversing the rotor rotation, we can change the phase sequence. By reversing the rotor rotation, we can change the phase sequence. If rotor rotation is reversed, then phase sequence also reversed. But there is no need of change of field excitation. There is no change of field current. Even though field current is same, by changing the rotor rotation, we can change the phase sequence. In alternator, by changing the rotor rotation, we can change the phase sequence without changing the field current. For example, if they ask you a question in synchronous motor, How we can change the rotor rotation direction? In synchronous motor, by changing the phase sequence, we can change the rotor rotation. No need to change the field current. So the conclusion is that, listen carefully, in alternator, by changing the rotor rotation, we can change the reverse phase sequence. In alternator, by changing the rotor rotation reverse, we can change the reverse phase sequence. If the phase sequence reversed for synchronous motor, we can change the direction of rotor rotation, vice versa for motor and generator. So our answer is, to get the reverse phase sequence, we have to change the rotor rotation without changing the field current. Right, sir. Next question. A single phase 2000 volts alternator has armature resistance 0.8 ohms, synchronous reactance 4.94 ohms. The voltage regulation of alternator. We have to find out the voltage regulation of alternator at 100 amperes, 0.8 power factor leading. 100 amperes, 0.8 power factor leading is. For this, we have to calculate first EMF. What is EMF? Generally, E is equals to V plus IAZS. How we can calculate the EMF? E is equals to 2000 at an angle 0 plus 100 at an angle. We don't know the angle, but we know the power factor. That's why 100 at an angle cos inverse of 0.8 into ZS. What is ZS value? 0.8 plus J into 4.94. This is our EMF. Take a calci and calculate this one with this 0 degrees and calculate this one. Then you can get the answer. 1822.314 at an angle 14.07 degrees. If you calculate this value, then you can get this value of magnitude with an angle of this. E at an angle delta, you can get the answer. By calci, you can calculate. If you calculate this value, you can get this answer. But they asked me voltage regulation. Voltage regulation is equals to E minus V by V, nothing but 1822.314 minus 2000 divided by 2000. If you solve this equation, you can get minus 8.886%. 8.886%. 885% actually, exactly. If you calculate 885%, if you calculate this value, you can get around minus 8.885%. Yeah, this is my voltage regulation. So which of the following is correct answer? 7 wrong answer, 14 wrong answer, 0 wrong answer. And generally the answer is minus 8.9%. But generally, we can get the answer directly without doing all this. If you have a good knowledge, if you have a good concept, directly we can get the answer by seeing the options. How, sir? They given that the alternator is operating at leading power factor. Generally, in leading power factor, in most of the cases, the regulation is negative. Most of the cases, 90% of the cases, the regulation is negative. Of course, in remaining 10% of the cases, 0 also possible, positive also possible. But in generally, the regulation is negative in leading load. Of course, we have a formula, we have a answers, and we can go through your formula, right? So after solving this, we can get the answer minus 8.88 actually. So they given the option minus 8.9 is 100% correct answer. Right, next question. Let's see the next question. Next question. It is desirable to eliminate fifth harmonic voltage from the phase voltage of an alternator. What you have to eliminate? Fifth harmonic voltage. Fifth harmonic voltage. The coil should be short pitched by an electrical angle of. What is the short pitch angle? To eliminate fifth order harmonics. Tell me the formula. Generally, short pitch angle alpha is equals to 180 degrees by n, where n is the order of harmonics. N is the order of harmonics. Then tell me, to eliminate fifth order harmonics, fifth order harmonics, alpha is equals to 180 degrees by 5. If you calculate 180 degrees by 5, you can get 36 degrees. So what is the electrical degrees to eliminate the fifth order harmonics? 36 degrees. If they ask you a question to eliminate seventh order harmonics, 180 by 7, 25.5 degrees. If they will ask you a question to eliminate third order harmonics, 180 by 3, 60 degrees. Like this is a very repeated question, very important. Right, next question. Figure shows the magnetization curves of an alternator. At rated armature current, unity power factor, and also at no load. The magnetization curve for rated armature current, 0.8 power factor leading is given by. 0.8 power factor leading is given by. Right, sir. See here. See, they given this is at no load and A curve B, curve C, and curve D. We have to choose one curve for same armature current, 0.8 power factor leading. Let's see, they given that this is the rated armature current at unity power factor. This is at no load. And this is at rated armature current unity power factor. But they asked me the question, rated armature current 0.8 power factor leading. So, leading nothing but the curve C. Lagging nothing but the curve D. You know already that. So tell me now, what is our answer? So the curve C represents the leading power factor magnetization curve. Curve C represents the leading power factor magnetization. Yes, this is the question for, this is the answer. Right, sir. Next question. XD, XD dash, XD double dash. XD is the steady state D-axis synchronous reactance. XD dash is the transient reactance. XD double dash is the subtransient reactance along the D-axis. This is the steady state, transient, subtransient. Steady state, transient, subtransient reactances along the d-axis. Respectively, which of the following is true? Which of the following is true? So, the steady state reactance is greater than transient reactance is greater than subtransient reactance. Or like this, there are 4 options are there. Now tell me, see here, before that, I draw 3 diagrams for steady state, transient, subtransient. Before that, we have to know what are the reactances here. XA, the armature leakage reactance. For example, XA, armature leakage reactance. XAD, the fictitious reactance, armature fictitious reactance along the D-axis. XFD, the field winding reactance along the D-axis. And XDD, the damper winding reactance along the D-axis. XA, leakage reactance. XAD, friction reactance along the D-axis. XFD, field winding reactance along the D-axis. Damper winding reactance along the D-axis. If we draw the diagram, this is the subtransient reactance. This is the transient reactance, subtransient, transient, steady state condition. In subtransient condition, in transient condition, in steady state condition. In subtransient condition, we have a damper winding reactance also included. But in transient reactance, there is no damper winding. In steady state, there is no damper winding and field winding reactances. So this is now XT double dash, this is XT dash, and this is XD. XD double dash, XD dash, and XD. XD double dash, XD dash, and XD. Now tell me which is greater, which is least one. Yeah, generally this is greater one, and then after this is, and the least one is XD double dash. Least one is XD double dash. So what is the answer? See, XD is the maximum value. XD is the maximum value. XD double dash is the least value. XD double dash is the least value. So this is our answer. So always the steady state is greater than, transient is greater than subtransient. Because in subtransient network we have a damper winding and field winding and armature. These 3 combination. So whatever, you have to remember this one, and these are the circuitry. These are the circuitry.